Hello, y'all. Welcome to lesson 93 of my DB chemistry curriculum. Today we're going over reactivity 2.3.7. This is an HL topic. We're going to talk about the equilibrium constant and Gibbs energy change, delta G. Both can be used to measure the position of an equilibrium reaction. So, one of the first things we have to discuss when we look at this is that when we have a reaction at equilibrium, we can make a couple assumptions. If the reaction's at equilibrium, this is the natural state where it wants to go. Therefore, we know that entropy is at its highest. Also, because it is spontaneously moving towards an equilibrium, we know that Gibbs energy is at a minimum. So at equilibrium, it is logical to see that we have a low Gibbs energy and a high entropy. If we were to look at two reactions and graph their progress, so we can just draw a graph here where we have Gibbs energy on our y, and this will generally be considered G, and we have our reaction extent, and on our left we have our reactants, on our right we have our products, and so we just look at the energy across a reaction, and I'm going to duplicate this because we'll do two examples. Let's say we have a spontaneous reaction. The spontaneous reaction is going to move towards the products naturally, meaning our products should have a lower energy than our reactants or lower Gibbs energy. This way the reaction will progress forward. However, equilibrium states that the reaction won't progress all the way forward. So we can kind of look at it as like a little hill or a little valley. And as the reaction progresses, it moves down that valley, and we have this low point. This low point represents, I should do a dotted line for that, represents our equilibrium, where Gibbs is at the minimum value. It is shifted towards the products as you would expect in a spontaneous reaction. This maximum is our Gibbs of reactants. This minimum, or at least the far right point, is our Gibbs at products. And we can see that there is a decrease where delta G is less than 0. So this is where we see a spontaneous reaction going from a high Gibbs energy reactant to a low Gibbs energy product. But because it's an equilibrium, it doesn't go all the way to the products. Furthermore, we can assume that our equilibrium constant Kc is greater than 1 because, as you can see, our equilibrium is shifted towards the products. Meanwhile, we can look at a different graph. So this time we'll assume a non-spontaneous reaction where our products have a larger Gibbs energy than our reactants. And in this case, we see the opposite curve. We have our Gibbs energy of reactants, and we have our Gibbs energy of our products much higher. We have an increase in Gibbs energy, so the change in Gibbs is greater than 1. And for here, our Kc is less than 1. Oh, sorry, change in Gibbs is greater than 0. It can be any positive value. Furthermore, our minimum Gibbs energy is once again our equilibrium point. We can see that it is shifted towards the reactants. So this is how we can use Gibbs energy to explain equilibrium. When you look at a reaction, you can kind of generally imagine a ball rolling down a hill, and it comes to this low point. That point it settles, that low energy is our equilibrium, and it happens in both cases, both a spontaneous and non-spontaneous reaction. So we can make some generalizations. delta G, Kc. So for these generalizations, if delta G is less than 0, Kc is greater than 1. Let's make that a little clearer, greater than 1. If delta G is greater than 0, Kc is less than 1. And if delta G is exactly at 0, Kc is probably equal to 1. On this first example, we have favored products. On the second example, we have favored reactants. In our last example, this is neither favored. So we can assume either from delta G or Kc which way an equilibrium will lie. The awesome thing is that we can actually combine these two to calculate delta G standard from Kc, our equilibrium constant. We have an equation. It is delta G standard is equal to negative RT ln K. And this equation actually looks pretty similar to parts of our Arrhenius equation. We'll see as we rearrange it a little bit. Furthermore, this reaction is also found in your data booklet, so you do not have to have it memorized. Now, the different parts are, this is our standard Gibbs energy. Standard Gibbs energy change. And this is in joules mole inverse, or actually this would generally be joules. Over here we have our gas constant, 8.31 joules Kelvin inverse mole inverse. T is, of course, temperature, and that's going to be in Kelvin as well. And lastly, we have lnk. lnk is the natural log of Kc, our equilibrium constant. You'll notice in this equation they refer to it as K. This has no units to it. Furthermore, if instead we have our Gibbs energy and we want to find K, we can rearrange to find K, which of course is Kc. K is equal to e to the negative delta G over RT. You'll see this is very similar to our Arrhenius equation, as we have Euler's number raised, but instead of our activation energy over the gas constant times temperature, we have Gibbs energy change. So with that said, let's put this into practice with an example before we close out this video. So in this example, we're going to be looking at the equation of nitrogen gas reacting with oxygen gas to produce, in equilibrium, 2NO gas. All right. For this reaction, we are given that the Kc is equal to 1.60 times 10 to the minus third, and this is at a temperature equal to 150 degrees Celsius. I see that degree Celsius and automatically know that I should probably be in Kelvin. Now, our job for this is to determine delta G standard in kilojoules mole inverse. So two little discrepancies we have to deal with. We have Celsius here, and we're looking for kilojoules. When we know that our equation gives us joules and takes Kelvin. So we need to make sure we remedy that by the end of our problem solving. So we'll go ahead and set up our equation. Delta G is equal to negative RT ln K, and then we'll plug our values in. Negative 8.31 times 150 plus 273 for the Kelvin conversion times ln, and K is 1.60 times 10 to the minus third. So when we plug this all into a calculator, you'll find that you get 22,630 joules mole inverse. Now, the issue that we said before, we already corrected for Kelvin, but we have not yet corrected for Joule. So we're just going to do a quick divide by 1,000 to get our final answer of 22.6, rounding for sig figs, kilojoules mole inverse. And that's pretty much it for delta G and the equilibrium constant. There isn't too much there, but I hope this helps and have a great day.